we always.
Hi! How are you? I'm doing great.
That's your eye.
It's feeling better. The other guy's pretty messed up though.
It's his son.
Yeah. You're the story. It's okay. We
All
don't
right.
have those days.
Yeah. All right, good to see you.
Bye, Mad Dog.
So yeah, whenever you get data that's deemed to be normed, these percentages fall into play. In stats, we do a lot of what's, you might have heard something called Z-score, Z-testing, things like that. It was on the part, wasn't it? It had like a Z-value. And that has stuff to deal with norming of data. When you're doing this, there's a lot of statistics that all it does is try to make the data normed. Because if you get normed data, it's a cool name. I have normed data. These numbers always fall. I got it in the head to remember things. These percentages always fall into place. Okay, and that's the kind of the cool thing about norm data. You were asking about which one? 30? So you're looking at, you have a norm distribution that has a mean of 64, so the average is 64. It has got standard deviations of 7. So that means I'm going both directions. I don't even have to put the curve in. And it's asking to go less, so I'm going to bring this down to 57 and then 50. And I want to be less than 2 standard deviations away. So I'm looking at these two right here. All you do is add them up. So then I get what? 0.025025. So I have 0.025, and then I want to do that 4 times. So I either multiply it 4 times out, or I just raise it to the 4th power.
Wait, I thought it was 0.025 times.
Oh, I didn't see that.
It means the same thing.
I didn't see that. Wow.
Yeah, it means the same thing.
Wait, what gives you?
Yeah, you get really, really, really small numbers.
7 zeros.
It's instead of multiplying it out 4 times, because we're to the 4th power, it means the same thing.
Oh, 6.
I think it was 4 times.
No, multiplying it out 4 times, and multiplying it 4 times.
Did you get 99?
I got 97. I got
You get-
0.97.
When we get to a value like this, which is what is on the past, I'll make sure that the calculator spits out a number. Fair enough. Yeah. I get a second question. Guys. You forgot about the other, after the 3 standard deviations, you forgot about the outliers, the tails. The tails aren't drawn in, or they're usually not filled in because it doesn't occur very often. I mean, we're talking less than 1% of the time you're going to get something in those values. So it's usually, it's just kind of like your, like I say, an outlier. It's that 8-foot tall guy and the 2'3" guy. Sir?
All this stuff on there adds to 1, right? So
Yep.
how come after 3 standard deviations, they just set it off the last 0.3%? There's no need for 4?
What do you mean? Oh, like the 4 standard deviation? Because once you start looking at after 3 standard deviations, you've already encompassed 99.7% of all your data. If you want 4 standard deviations, you're talking like 99.99999. It's just, yeah, you've already had, it's already such a small percentile that's there. There's no need to break it off any further.
Oh my god, our test is Thursday.
Okay. So what we want to do here today is I'm instead of doing the fun stuff in the middle and forgetting how to do all this math stuff, I'm going to put the fun probability thing on Friday because going into a weekend we got some fun things to do. I know that one of the projects, that's not going to say projects, just these fun experiments that I have that we'll look at. One of them is like counting principles, trying to figure out different ways that you can create your own passwords to computers and how you can hack them. Another one is how can you buy a lottery ticket and change in your pocket, and then maybe we'll do an actual lottery draw to see who wins. Because you guys, I don't know, $1 million. I'll make $1 million bill.
No, you should go like hardcore on it, like on Word and everything for you all.
Like $1 million.
And then the last thing we have is about doing like a statistical study to see if you have ESP. It's when you're gonna pick a card and you're gonna guess what it is.
I think we've proven Hannah does not have it.
Proven nobody has it. But I talked about with the, if you have a deck of cards, you want to bring it, that's cool. Otherwise, I found an app that will randomly draw cards. If you put your phone down, you pick it up, there's a card, put your phone down, pick it up, there's another card. It's kind of like the Magic 8-Ball kind of game. It's kind of cool. So we'll do that on Friday. No, you need to stop the blackjack.
We stopped with the blackjack. Got rid of the app.
Good for you. Good for you.
Yeah,
Cookies.
what is Hannah?
What's up?
No.
We never tempt an addict to
Yes.
listen.
No. Doesn't always have to be a winner.
What happens to that money if
Controls.
So there's a couple of other bits in this section that we're going to add to what we did last night. The last little bit in here talks about the idea of norming data. And we've actually been doing this with our binomial distribution functions. When you look at we're going to add to it. When you look at, when we were working with binomial distributions in the past couple of days, we were working with that Bino M PDF and the Bino M CDF. And it was adding up all the cumulative stuff for us. Now, what we're going to look at now is, instead of doing all of this junk, a real nice application that we use in the calculator for when your n value is large. When you have a large binomial distribution, it is very, very close to being normed data. Okay? If the binomial distribution looks clean, it norms itself out. We kind of started showing that with some of the histograms. The more n value sets, the more it looked like the actual bell curve. Yes, ma'am?
I just remembered
And when we use that button, that CDF button, it was the cumulative distribution function. It was summing up everything to a certain value. We can actually use that with binomial to show that it's normed. So let me show you what I'm talking about. When you have a set, like this, and they're talking about, there's a poll that was done, 29% of people know somebody or play soccer themselves. So if you conduct a random survey of 238 people, which would be considered an n value that is large,
we're not adults, so.
but that they or someone in their family.
Not knowing.
But it says then, what is probably that you will find at most 55 people who come from the family who plays soccer. So here's what happens. What is our n value here?
238.
Our n value is 238. What's our p value? And this is asking us at most 55. Isn't that a k value? Do you see how this sets you up for using that Bino and CDF? Because it'll add everything from 0 to 55 in the calculator. This book was written, obviously, prior to when we had that functionality in the calculators. It is going to have a slight difference of the rounding error as opposed to creating it and norming it to a specific standard deviation from the data set. But for our intents and purposes, it's close enough. We're talking thousands here, guys, a couple hundreds maybe. It is really, really, really close to an approximation to make it work. So all we have to do here is know that the Bino MCDF, we all know where to find that now, right?
Yes.
Second bars. And then we would put in our calculator parentheses N238, comma, P, comma, 55. And it's going to give us a percentage.
or decimal, excuse me. All right. What is it rounded out to be?
0.0248.
It rounds it out to be .0248.
Yeah.
Okay. What's that? Okay. If you look at what the book did, the book normed and found out a standard deviation, and it was within 2,000s, excuse me. CDF is close enough. Yeah.
Is that .024?
Yeah. Cool. It says the number of people being surveyed, they gave us a percentage, and they told us how many successes we wanted. We wanted at least, or at most, 55. Now let me ask you this. What would you do if it said at least 55 with the same set?
54 and then do 1 minus 7.
Good. Remember, the Bino CDF is NPK for when K is less than or equal to some number. Okay. If it is K is greater than some number, then you have to do 1 minus Bino MCDF of NP, and then what do I do with K?
You do the number less than the number.
The number less than the number. Yes! K minus 1.
The number less than.
Yeah, then you work in the complement.
You forgot the
Because-
second bracket. Thank you. I know, you got hit in the head.
Say that. Okay. So what for our goals and things like that, when we have binomial distributions that are large, you can say that it's more, right? And you can use the same ideas, and then we can do this stuff. Then it'll work out just as yeah.
At what point is it considered like large? More than 100, more than 200?
I think they set some basis for it, but they really actually say when your n value is usually when the n is large. Let me show you this one. This might help a little bit. Wait, what?
Oh, what's the normal PDF?
The normal PDF one would be the one that we would use to send to our list, because that one will calculate the value for each individual success. Came through, if this was one where we had,
Yeah, I know, but I thought, isn't that just binary?
yeah, then that one would give us,
No, it's normal instead of binary. It's a whole different thing.
Yeah, on like the calculator,
Normal PDF.
if you put second bars, the top two.
I don't know, Google it.
I'll do it.
Is there a difference between the second catalog and second bars?
There's more stuff in the catalog.
A lot more stuff than catalog.
Are you sure it doesn't
I'm
matter?
Googling
No,
it right
whichever
now.
one is faster to get to. I mean, I've been going to bars as quick as these go up.
No, and then we need to find out the numbers first. Second, bars, and then, A.
What's your, what's your
No, I would just do 55 minus 1. Because if I wanted to do at least 55, that means it would be K greater than or equal to 55. So in order to find out the values that are greater than 55, going up to our n value, I'd use my n, p, and then K minus 1, which would be 54, and I'd find the complement of it. Because this is, when I do this is taking me all the numbers from 0 to K. When I do this, it's giving me all the numbers from 0 to K minus 1. And if I subtract that from 1, it's going to give me everything else on the way to n. Does that make sense? All right. Kind of a weird little playbook how that goes, but that's if you're using the rules of complements to affords you those values. Okay? Let me show you this. Well, Google it in a minute. Let's do this first, and then we'll figure out what that does. Take a minute, and I want you to do these three. Using the same idea that CDF, because look at your end value here. Your end value is large. It's 460. All right? It's decent, yes. So take a minute, do those calculations. It is so much easier than what you're thinking.
Really?
That's it.
Oh, wow.
Think about what this is. You're going from 0.
18 minus 6 is 12, and there's a 12.
No.
Yes.
Hold on. This is 0 to 18 is k is less or equal to 18. Correct? Okay. Now, here's 6. Isn't that k is less than or equal to 6? Oops. If I take this out of here, aren't I left with what I need? Just subtract the 2. That's it.
You're right.
Right, because I can't just tell you what to do.
Oh, it's 60.
I can't tell you what you need to think.
I was asking if that was so like the value.
Oh, no, you just kept saying, I don't know what to do. Well, I can't tell you it. That's what I'm trying to say. Draw the number line, look at what those values are giving you. Think about what that binomial CDF does. It sums it from 0 to 18. And if you sum it from 0 to 6, well, all I want is between 6 and 18, is back out the other part.
I was confused because I was thinking because in the first one, 16, it was, it's a really high number. So I was thinking that from 0 to 6, it's going to be bigger than 6 to 18. So it would, when we subtracted it out, it would be.
Don't assume. Think about what these functions do. That CDF will sum you from 0 to 18,
Yeah.
and then it'll be 0 to 6. If I take out that 0 to 6, I'm left with between 6
So,
and 18.
K's less than 8.
That's all that
Yeah, you're right.
So you take your bino,
I wrote the values different. 1, 2, 3, 5, 6, and like.
remember what it does. Going from 0 to 8, going to the CDF of 18, takes you, adds everything up from 0 to 18. And if I subtract out what goes between 0 and 6, aren't I left with what's between 6 and 18?
Yeah, sure.
You know what I mean?
I did that. Is this
Yeah,
all wrong?
it's
I did.
Oh.
Allie, what'd you do? No, I did it the wrong way because I did 8 and 6. I got 0.8. I got 0.811. I wrote the wrong numbers down.
Now, one of the things I will tell you is that by using this binomial CDF function, remember I said that it's slightly off to finding its own standard deviation. Okay? It's slightly off from when the way that the book does a calculation of standard deviation within the set value. It's okay. It's close enough. Okay? It's close enough. The answer in the book, I think, was what'd you get, 0.811? I think the book said 0.83. So, I mean, it's close enough. Seriously, it's close enough for what we're looking at.
Why is it off?
Because the way that they want you to do this is that they want you to find the actual standard deviation of the set, given the fact that you have an n value of 460, a p-value of 0.02, and then your n trials that you're looking at. You can get those values and norm them a long process. So we don't need, I mean, it's not that difficult, but it's a lot more work for what a very rudimentary idea of how statistics.
Right. The other one?
The other one is more right, but for us, it's allowing us to be able to use that CDF value kind of like with
No,
confidence
that makes no sense.
and with the other things.
What?
We have to disagree.
Come on. That was
Sorry, my eyes really hurt all of a sudden.
It was just like kind of
That too. No, my eye just twitched, it really hurt. Sorry.
That's how I feel about math too.
All right, let's do these then. We'll start on 41 through 55.
We're just adding these on.
Yeah. Same, it's the same page, what, 750?
Yeah, try these.
Are we doing all of them? Yeah.
We can just add it.
Yeah, please, just add them right to where you're at, and I'll leave this one up here so you can start
Save the
going.
planet.